We have Milad here with us, who is an intern on our team, working mostly with Nicole and I, and also with Shuang and Abradeep. Milad spent the summer doing some privacy analysis of DP-SGD, I guess, thinking about how, like, what properties DP-SGD has, and if we can lower bound privacy. And he was able to get like far more than we sort of hoped we'd be able to achieve, and has a bunch of really interesting results. We're writing for a paper to submit to Oakland, and Milad, feel free and go ahead.
Sure. So I'm going to give a brief summary of the kind of my findings in the internship and kind of overall results. So okay, so kind of the whole goal of this work is to kind of find the relationship between the privacy guarantees that DP-SGD gives us to the kind of practical adversary. So you want to find if the DP-SGD bonds are tight or not from the adversary point of view, not from the theoretical side. So we know that the differential privacy in general assumes a very powerful adversary and tries to give the theoretical bounds for that specific adversary. Now the question is, can we be that adversary? And we try to use the kind of assumptions that DP-SGD uses to build that adversary and evaluate the bonds in these settings. In general, why this is kind of in this type of research is useful. First of all, we can see if the theoretical bonds are tight in a practical setting or not, which is kind of useful for both practitioners and kind of theoreticians. And kind of we can see which sort of assumptions are very important in from the practical point of view, if the adversary has access to which part leaks the most information for an adversary. And we can see that kind of in a settings, in a places that we don't have a theoretical kind way of analyzing the privacy leakage, we at least can get an approximation of the an approximate understanding. Can we kind of get an idea of how much are we leaking? So that's kind of why we are even doing this research. A general setting for my work is that we kind of try to evaluate the DP-SGD. So what does DP-SGD says that we have two databases, D and D prime. They are different in exactly one instance, and it says that if you train two models on these two data sets, the output and these two models will be similar up to some small error bands, which is defined by the epsilon and delta. And now our setting is to create an adversary to create these two data sets and create an adversary to distinguish between these two models. So we want to. So our goal, our objective is to create these two adversaries. And so I talked about the DP-SGD uses several assumptions, and these assumptions are something like DP-SGD assumes that it doesn't even look at the problem as a machine learning model problem. It's just look at it as a set of gradients and try to kind of be gradient vectors, try to make those gradient vectors a private vector. So it doesn't have a kind of any assumption on the input says that gradient. So we can assume that adversary can control the gradients, not the input. It also assumes that the adversary can look at all of the intermediate steps. So we have these settings of Whitebox access to the model, which adversary can look at each gradient update, which might not be as practical, but in a settings like a FedSGD in a federated learning, it can be possible to see every updates in the in the updating of the model, or we can adversary can have an API access or black box access. And also it says that for every kind of data set, for every model, we have these sort of bonds, theoretical bonds. So we kind of see what happens if the data set is malicious or the model is malicious. And a set of other kind of assumption, like it uses subsampling and kind of uses the independency between each samples to compute the sensitivity and these things. So these are the sets of assumptions that we are trying to evaluate. So kind of our main methodology, as I said, is that first we craft two datasets, D and D prime. We train a model on D or D prime, and we use an adversarial method to an attack model to kind of distinguish if the model was trained on D or D prime. So it's a kind of the general framework is like that. And then we kind of compute the false positive and false negative, or false alarm and misdetection of this attack as to convert it back to an epsilon bound. So how does we do that? How do we do that? Is that we know that if a mechanism has a epsilon delta differential privacy, the false alarm and the misdetection is bounded by some amount, and we upper bounded by some amount, and we use that to kind of lower bound the adversarial the epsilon, the practical epsilon. And our goal of our general the attack is to maximize this empirical epsilon, and we also find we use a Clapper-Pearson to kind of find a confidence on our kind of assumptions. Yeah. So let's start with a very simple attack. So the kind of the most popular attack currently in the community is called membership inference. So it's like we have two datasets, D and D prime. The adversary selects one instance from the test dataset and adds it to the training dataset. So like the 7 in this example. And we train two models on these two datasets. And the idea of the membership inference usually says that the loss of the model given that input is different if the model was trained on that specific input or not. So in this case, if a model was trained on D prime, the loss would be very small. If it's not, it will be a bit larger. And to frame it back to our kind of setting, we let the adversary to select the hardest test instance, and it usually, iterates over all of the instances, find which one works the best for this setting, and we look at the loss to distinguish between if it was trained on D or D. And when we do all of these things, we do the hypothesis testing, we compute the false positive and these things, and convert it back to the epsilon. We get a result like this, which is not good looking because the theoretical bounds are way more than the practical bounds that we get from this. So this result can have a two type of interpretations. Either one way of thinking is that the DP-SGD bounds are very loose and they are overly pessimistic, and it's not in practice they gives us a much better privacy guarantees than the theory says. Or we can say that this attack is not a good attack. This is not a good attack to evaluate DP-SGD. So as the title of this talk suggests, this is the true interpretations. But I'm going to walk through the steps that we go through to reach this conclusion. So
Milad, before you go any further, do you want to pause to see if anyone has questions on the setup that you have gone through? Because this setup is sort of critical to his work, and so if anyone has questions on how the setup of this works, now would be a good time to ask. Okay, I guess you did a great job of explaining it then.
Hopefully. So to kind of evaluate the DP-SGD bounds in a more for a better adversary, we first of all look at the inputs that the adversary adds. In the membership inference, the adversary just look at the test dataset and select one, which is a random sample from an underlying data distribution. It might not be the best example to add. So instead of adding an average sample, we try to find the worst sample that we can try to do a malicious example, and we want an example such that if a model trained on that specific example, the output would be very different if compared to case when it's not trained on it. And we know from the current, trend of works that, for example, adversarial examples is a good example, is a good way of generating those things. We start by a normal image, we add some noise to it, and kind of we get a very bad looking example. And again, we look at the loss of that example to kind of see if it's part of trained data. So if I want to give a kind of a visual way of looking at the problem, is that we have the MNIST dataset, we have the MNIST dataset plus a weird looking sample from the MNIST dataset. And the idea here is that if the model is trained on that specific example, the loss would be low. If it's not, the loss would be much higher than a normal MNIST sample. So, and this is an easier way of kind of distinguishing this thing. So if we convert this back to a kind of a practical epsilon, we see that, okay, that we can significantly improve what the kind of from compared to an average case from the membership. So we can see that there are ways to improve that. So kind of there are some evidence of the DP-SGD being much tighter than we thought before.
So Milad?
Sure.
I had a small question. I was earlier trying to find the exact question that I should be asking. So like your setup and the objective of like how tight DP-SGD bounds are, it reminds me a lot of a talk that Matthew Jagielski gave a few weeks ago here. Like, is it easy to distinguish, or like what? Yeah, I'm just trying to understand what is different. Like there was also some poisoning there, I remember.
Sure, yeah. So the kind of the Matthew was kind of trying to find audit the DP-SGD from a black box adversary. We try to see which assumption in the DP-SGD has the most effect on the kind of adversary's point of view, and kind of see exactly look at the assumptions themselves individually, not just look at the DP-SGD from a black box point of view. So we try to create a specific attacks for a specific assumptions. Yeah, it's kind of that.
Hi, Milad,
Okay.
it's Steve.
Hi.
Just out of curiosity, why are there sort of, discontinuities, or not discontinuities, but sort of jumps in this graph here?
So it just, the one problem in general that we are going to see in further slides is that we have a limited number of runs. So for example, we have 500 or 1,000 runs for each graph. So if you change, if the adversary detects one or kind of labels one true or one example correctly or incorrectly, then the difference in the result is too much. So there are a lot of jumps in the graphs. And yeah, that's kind of the general kind of the reason why we have multiple jumps in the graphs.
Thank you.
So in a black box setting, when we only change the input from the average case to a malicious kind of worst case example, we gain much better practical upside. But kind of the DP-SGD assumptions never ends there. That kind of the next step is that kind of here is what makes our work different from Matthew's, is that DP-SGD has assumes that the adversary looks at every individual steps, not just from beginning to end. So this allows us to, instead of looking at the one loss, we can look at all of the loss in the iterations. Not only that, it also allows us to change the kind of the the malicious input in each step. So one way of doing that is to repeat the kind of the adversary example creation in each iteration, which was very costly for us. So we kind of come up with a different mechanism. in this mechanism, we assume that we have a query image X prime, but we try to create an image X such that if a model trained on that specific image, the output of the model for X prime will be different. So if you look at the formula here, we want to create an image X such that f of X prime will be different if from the case when the X was part of the training data or not. So to give a kind of visual kind of understanding of this, we have this query image 4, but we create a function of that image and we add it to the we create a different version of that image and add it to the training data set, which we can change in each iteration. And instead of just looking at the loss in the last iteration, we can look at the loss in each iteration, in each iteration of training. In each gradient of that, we look at the loss, see what happens for that query image, for that 4. So when we do that, we see that, okay, we can significantly improve the practical epsilon that we get on the lower bound of the epsilon that we get compared to just looking at the beginning to end. So this is right now just says that, okay, whitebox access is very important. If an adversary has a whitebox access, it can just gain a lot of unintended information from your trainings up to the theoretical bound of the DP-SGD. So this is, until now we have a good result that, okay, DP-SGD are tight, but we can go further. We can go, okay, I said that the DP-SGD assumes that the adversary has access to the gradient, not to the model input. So we can use these assumptions to create a specific attack for it. In this attack, again, we try to, instead of just looking at the model output for a given input, we try to look at the model parameter themselves. We try to embed a specific watermark or pattern to the model parameters, and we try to look for that specific pattern. So the pattern we chose for this attack is very simple one. If it's easier to show it here. If we have these model parameters, we try to pick 2 model parameters, and we try to make them as far make the distance between these 2 model parameters as much as possible. So we try to maximize the distance between these 2 model parameters, and it's instead of just unlike the previous example where we added this sample to the test data set, here we are adding a gradient vector to the test data set. And the gradient vector has this kind of property that the distance between the 2 specific model parameters is very high. And we also do the clipping and all of the things that DP-SGD does to this gradient to this gradient. And so the adversary looks at when the adversary wants to find out if an example trained on D or D prime, he kind of gets compute the distance between these two specific model parameters and make a decision based on it. So in general, if the distance is high, then the adversary has it says that it's from D prime. If it's low, it says D prime. So when we apply this attack, we can see that we can improve the results again from the input to the gradient when we go from input to the gradient, but the improvement is not that much. We can improve. We can again for this setting we only assume that we can look at the black box, so from the beginning to end. But if we look at every intermediate steps as well, we can kind of improve it furthermore. So just the trend that we are seeing that by adding each of the assumptions in DP-SGD to attack and designing a specific attack for these assumptions, we can get very similar result compared to DP-SGD. And kind of a general interesting result of our experiment was that if we used a very large epsilon, our attacks was always successful in all of our runs. So for epsilon large and 100 or 120 was the attack never failed. So it's a good thing that, I mean, it's a limitation of the this work that we cannot get for example, this large epsilon, but it's kind of we are limited to computational power. And then again, so by now we kind of have very tight attack to DP-SGD, but kind of we try to evaluate all of the assumption in DP-SGD. So one other assumption in DP-SGD was that the malicious the dataset can be worst case dataset. So we want to create a very malicious dataset for to take advantage of that kind of assumptions. So to do that, we take the normal MNIST model, we take an initial model from whatever neural network model we want to train, and we set the labels of that images to whatever the initial model predicts. So when we do that, then the loss of the model with respect to the loss of the model parameters would be 0 given these inputs. So if we do that, and when we combine it by our gradient attack, we actually remove all of the unintended noise from the input data set, and we get a very close attack compared to the gradient ones, to the DP-SGD ones. So if we look at this graph, we can see that for a very small epsilon, the attacks is just same values as the DP-SGD predict. So it's a very good result because I mean, it shows that the DP-SGD bounds are very tight. But and also this says that it's not that if the adversary can modify the training data set, can leak, I mean, very large amount of information from the data up to the DP-SGD bound.
Sorry, Milad, I missed this. What is the green line?
So the green line is just the confidence interval from the attack. So we compute the average case, which is the orange line, and we compute the 95% confidence in lower bound from this.
Okay.
The confidence interval is usually very dependent on the number of trials we have. So if we have more trials, we get much better results. But
okay, thank you.
And for this attack, kind of if the epsilon was larger than 80, we kind of was always successful. So, but if you look at the graph, you see that for up to something like 3, we are very close to the DP-SGD bounds, but for epsilons more than that, we are kind of not that close. So what's the kind of problem with that? To kind of find out what's going on, we created a very specific dummy example where the dataset size is 1, the sensitivity is 1, we only train it for one step. It's kind of very stupid setup, but the benefit of this setup is that we can run it for several times. So when we did that, we ran it for 100,000 times. We got the result that, okay, we can get the results are again similar, but for a larger epsilon. So for a smaller epsilon, we are very close to theoretical bounds. But here, instead of 3, is if the epsilon goes from after 4, we are kind of go away from the theoretical bounds. So that kind of we found that the reason for that is that the kind of the DP-SGD bounds are usually in the tail of the distribution, and usually the probability of that worst case happening that the DP-SGD bounds is less than 1%. So if you want the epsilon of, for example, 5, you would need to have at least many runs, a lot of runs to kind of get it. So we kind of find it if we want an epsilon of 15 and we want to get a theoretical, practical run similar to that, we at least need 10 million runs. So with 10 million runs, we get epsilon similar up to 50. But so the problem with this approach is very computationally intensive. It needs very computation we need a lot of runs to kind of see the bonds, get a good value for the bonds. So yeah, that's that. And so the kind of these things was kind of DP-SGD and seeing the DP-SGD, is it DP-SGD tight or not, which we saw that if the adversary has access to that, has a very tight bound. But kind of another spectrum of kind of these attacks is that can we use this sort of evaluation in settings that we don't know how to analyze the privacy. So one specific example that we thought was the batch norm. We saw that batch norm has a very good effect on the machine learning kind of models. But kind of the problem is that we currently doesn't know how to analyze it by differential privacy. And we use this approach of differential training and try to have an adversary to distinguish between these two. We saw that our adversary can get up to 100% accuracy if you use a just normal batch norm. So kind of as a result, it's not private. You cannot use that batch norm with the DP-SGD. It's just leaks information. So that's one way of kind of looking. Another way of looking at the kind of this method of the evaluating. And another question that we got was, how about the non-private method? What happens if you train a model normally, but you don't add noise? Is it private or kind of not? So we saw that if you don't do clipping, you don't add noise, the attacker can always win. So that's a kind of thing that if you don't do any of these things, the attacker can just add one sample which has a very large gradient and just destroy the whole model. But in a case that we only have clipping, if that adversary has a white box access, then it again can always win. But if we assume that adversary has a black box access and it can only add one malicious instant, we kind of get some empirical epsilon, but I mean, the values are too high to be good for a practical setting. So it depends on kind of your setting or number of training data set you have. But we saw that without adding noise, it's not good. I mean, the adversary can still gain a lot of information if we can add input and malicious input to the training data. And with that, kind of the overall way of looking at results is that when we have a theoretical epsilon, if we have a worst case data set, the results are very similar to the theoretical epsilon. When we have a gradient attack, we can see the different spectrum of the result from the theoretical to kind of the only changing the training data set by removing one instance or adding one instance from the training data set. So if the adversary has access to can change all of the training data set, can have a very bad effect on the privacy. If the adversary can look at the gradients and kind of change the gradients, again, can gain a lot of information. If the adversary kind of only can change the data, the leakage is much lower than the kind of the gradient, but still it can get a lot of information. And kind of if the adversary doesn't have a white box access, only have black box access, it's more limited. But yeah, so there is a kind of different, given the different assumption, we can see different values of the empirical epsilon. And for different values of epsilon, as we saw before, for higher values of epsilon, it's usually harder to get those values. So for a value of epsilon 4, the difference will be much larger compared to before. And with that, it's kind of a summary of my kind of internship work is that, first of all, DP-SGD analyses are tight in settings that they assume that adversary has access to all of these things, that the current theoretical bounds are tight. So it's not possible to. I don't think it's possible to improve the results by improve the DP-SGD by just changing how do we analyze the setting. So we should kind of add or remove some assumptions to the analysis if you want a better kind of analysis, a better privacy for the noise we add or something, or better utility for a specific number of value of epsilon delta. And kind of that we saw that the average case privacy leakage is much lower than the theoretical one, and the worst case that theoretical one assumes. And we saw that the non-private trainings are not private, which is not surprising, but at least we have some sort of a empirical evidence that that's true. So yeah, with that kind of I conclude my talk.
Great, thank you. So questions?
Hey Milad, this is Om again.
Hi.
Really cool work. I don't know if I should be happy or sad to see DP-SGD cannot be improved by a lot. But I had a couple of questions. So the first one is I was trying to wrap my head around this phenomenon that when there is low epsilon, so you add a high amount of noise, you can achieve attacks that match that bound. But when you add a lower amount of noise, somehow the attacks don't improve by that much. Is that correct?
So yeah, so the problem is not the attacks. So for example, if we want an epsilon of, I don't know, for example, 10, we have to run the experiments for at least e to the power of 10 times a lot of numbers, because not every case is the worst case example. So if you want to get this ratio of the e to the power of 10, you have to run the experiment for, I don't know, 10 million times to get a good value of epsilon. So we are limited at computational power, not the attack is not limited. Just if you run these attacks for infinite numbers, you always can just get the same values.
I see. So to get that bound of the exponential blow up, you have to repeat multiple times. Is that okay? And the second,
just that I just want to say that as you saw that kind of with 10,000, with 100,000 we can get up to 5. With 10 million we can get up to around 15-ish. So it's like it's a exponential number of experiments that we have to get if we want a better. And after a while, just you always succeed. So it's kind of like infinity. Then it's hard to kind of that. It's like a mostly computational problem.
Makes sense. And the second small question I had was in the data poisoning attack. You mentioned, so by Whitebox access, you mean that the adversary has access to all of the model updates, right? So I was wondering, like, if you insert a poisoned image, is it necessary to have all of the updates, or it's just enough to have like one update every epoch where the poisoned example showed up? Like, does the adversary?
Yeah, so the problem is that if you assume that you know which update is that when you added that image, you already kind of broke the DP-SGD assumptions. So since we the kind of you added that image by a random chance, you don't do shuffling, you just subsample every time. So you don't know actually which of these updates are that one that the image is included. So you have to look at all of the updates, not just. I mean, you don't know which one are those that example are added.
For sure. Okay. Thanks.
Sure.
Milad, can you comment a bit on perhaps using your analysis as a way to do unit tests for models that are trained with DP?
Sure. So that's kind of a good approach. That at least for a batch norm example that we saw that, for example, if you do that, if you apply this approach of the gradient update, gradient attack in these settings, you can see that, for example, if you run just DP-SGD with batch norm, it gives you some epsilon. But if you do our attack, you see that epsilon is not true. So it's a good way of kind of doing a unit test for find out if your method is actually differentially private or not. It gives you a lower bound on that, but I think it's a good way of do a kind of test to make
But it's going to be a very computationally expensive.
Yeah, it's computationally expensive. But for at least for small values, for less than 2, 3 is good. And I don't think epsilon values of more than 2 or 3 is good, because epsilon to the e to the power of 3 is a very large number by itself. So you are leaking a lot of information.
Milad, this is Abhijit here. I have a couple of questions.
Sure.
Question number 1 is, you showed it for MNIST.
Yeah.
Do you think this you could find out like this kind of adversarial examples in other data sets?
I have the already result for CFAR, but the problem for that I didn't include is that I don't have enough runs to have a good graphs. But it works for CFAR at least until the result I have right.
I see. So it does work for. I mean, the results are the theory remains the same. And the second question I have is this is more of an exploratory question. So you looked at DP-SGD, right?
Yeah.
So if I give you a different training procedure, something like, let's say, privacy amplification by iteration for a convex model, then if I run the process, your privacy for the first sample actually increases, right? Can you capture such a phenomenon with your lower bounds?
Yeah, so that's kind of to see that when we see that from the kind of black box to white box, we see a difference in the epsilon.
No. So what I'm saying is, like, if you run through the process, we know that the model at ith step actually is more private for a data sample. Let's say it was used at the first iteration, at the ith step, versus, let's say, I prime, which is much lower than I.
Yeah.
So as you run the process, the privacy of some of the data samples become much stronger for convex problems.
Yes.
And we know how to prove that theoretically. I'm just saying that,
yeah.
Can you empirically kind of show that this phenomenon is also captured by your technique?
Yeah, I think that's kind of, if we can create a worst case data set as we have here, it should be possible, because that's 2 points on a kind of a convex model. When you add noise, you just don't add kind of gradient to them, just add noise at the standard deviation. So I think it should be possible to show that.
Yeah, so basically what I'm alluding to is, like, there are different ways of training differentially private models. DP-SGD is one of them.
Yeah.
Does your technique extend to other techniques of training?
I think that's, I'm saying, at least for the amplification by iteration, I think we can just use the similar approach to just do that.
Yeah, so that would be cool.
So Milad, you've maybe touched on this. I may have missed it. In the plots that you showed, there was a point where things are tight, but if you keep going in the training process, then there is a gap.
Sure.
You may have explained this. Can you?
So I said so the problem usually is that number of the iteration that we run the experiment. So up to some value of the epsilon, if you, for example, if I run the experiment for 500 times, 1/5, if only the adversary they classify one image, one run by mistake, is 1/500, which is around 2 point something, 2.8, 2.76 something. But after that, it's like infinity or 1 or 2, I mean 2.5. So we are very limited by the number of runs that we have. So for the graph, that's why up to some point we are very close, but after that we kind of fall off, because I cannot plot infinity. I just always pick the next value over the infinity. So that's why kind of we have this kind of in some regions we are very tight, in other regions. I have some other results that we run for. I kind of have the hypothetical scenarios that we run for kind of more much larger runs that we are tighter in a larger kind of settings.
So just a follow-up for that question. So what then if we start with very high noise, like our starting epsilon is very low, then I guess so after the same number of iteration, we still have probably a low epsilon where I guess your attack can still handle. So in that case, do we expect to see a pretty tight gap between the theoretical and the practical, or is that?
Yeah, that's kind of the kind of experiment that we done. That kind of if you have a very large noise as a result, very small epsilon, you can get a very tight kind of.
I see.
Maybe a good way of thinking about this is just that because of how, like, if you were to do 10,000 experiments, like, and all of them succeeded, you can only get a 95% confidence interval of epsilon, like, I don't know, 4 or something.
Yeah.
You just can't get better than 4 with 10,000 experiments. If you want to get better than that, you'll need like 1,000,000 experiments. And at a certain point, like, you're just not going to get any better than this just because of the way that the math works out.
Yeah.
Yeah. Question. Nice results. I'm not too surprised by the result on batch norm. At the same time, I don't quite know what to do about it. Should we stop using batch norm? Should we tweak it, complement it with something else? Or what do you think?
So I think there are some ways to actually make it differentially. At least we can try to make it differentially private. So if we try to, there are ways to take an average in a differentially private manner. So we can try to take an average, to use the composition to add it to kind of to get the overall overall epsilon for a DP-SGD, for example. Compute.
Yeah, have people tried that, and did they get reasonable accuracy?
I tried that. I didn't get good accuracy, but I didn't I just tried one method and didn't put that much time. But maybe it's what.
Interesting. Thank you.
Maybe Milad, I'll ask you to speculate on what's next. Like, I really like this line of work, but what do you think is like good potential things that are consequences of this, or what happens now that we know that we can analyze things and become mostly tight? Like, what applications of this do you see, or what other research do you think this opens up?
So I think one kind of general good approach is to change how the membership inference attacks kind of work right now to this type of attacks. Try to, instead of just taking an average over all of the, I don't know, examples in the training data, try to kind of find the worst case example, try to add it to the training data set, see how much do we leak. And as the Peter suggests, it might be a good way of kind of do it unit testing, kind of see how much do we leak in a kind of these different settings. And kind of, I think it's good to kind of extend to other. So we only kind of look at the DP-SGD assumptions, maybe as kind of see if other methods of differentially private training or other assumption like the subsampling or the things that like different models and these things to different models, so that see the effect of those things.
So I have a question, I guess, for the people who are good at proving these, who do this kind of analysis. I have a sense, and maybe I'm wrong about this, that we prove things with such strong assumptions because that's what we know how to do.
Yeah.
Do we know how to relax the assumptions a bit and, prove things in that setting, or would that require a lot of building new machinery from the ground up?
I think Abradip is the best person to answer that. But kind of with the current way of analyzing, I think we cannot easily relax these assumptions.
So, Steve, what do you mean by assumptions here?
For example, being able to see all the intermediate gradients.
I see. So the bad news is that even by seeing the alter intermediate gradients, DP-SGD is actually tight.
Yeah.
So for convex problems, it is tight. I mean, so for at least for convex settings, we do not know a distinction in the sense that looking at all these gradients actually does something worse for you.
But as far as in the non-convex setting, Milad's attack works substantially better when given access to all of the intermediate updates versus just the final one.
Right. And the problem with any differentially private algorithm, designing any, analyzing any differentially private algorithm is that you need to know what the final model is. Like you need to understand some mathematical property of the final model. And the moment you go to non-convex settings, almost surely you don't know what is happening. So arguing about the final, okay, let me state it this way. We know how to argue about the path of the optimization, but since we do not know what the final optima looks like, we cannot argue about it as of now. So it would require understanding of deep learning itself. I don't know if it makes sense.
So in the same vein of Steve's question, maybe a different question about how hard it would be to analyze. Right now, the assumption is that you can provide an arbitrary, like you can feed arbitrary malicious gradients. Like that Milad uses this. Like if we could restrict them to be like valid gradients of the function, is there like a way to analyze this?
This is something which I don't know Keith is on the call or not. Keith Rush, myself have been discussing this. So this is a very good point. We do not know how to do this. So to rephrase what Nicholas, you were saying, not arbitrary sequence of vectors form gradient of a function. So if we can restrict our even the noisy gradients to a set of vectors which come from the gradient field of a function, maybe we can do better, but we don't know how to analyze as of now. This is a good question.
Okay.
Does it make sense?
Yeah.
So just out of curiosity, I wonder, like for the models you trained, how are their accuracy?
So for the kind of data poisoning models, just normal accuracy, just 90 something. For a gradient are very similar to it. Just as long as I don't change the whole training data set, the accuracy doesn't just go down because the whole goal of kind of gradient attack is to pick points that are not affected by normal training model instances. So you don't kind of destroy the kind of the objective.
Any final questions for Milad?
Thanks again, Milad.
Thanks a lot.